In this video, I'm going to take you through the hanging mass version of the Carcliff VPython program, and I'm going to take you through pretty slowly to make sure that everything in it that you need to worry about right now makes sense. If I get a chance, I'll put up more of an express version, but for now this is the version that we're going to have. I'm going to skip over some things that are going to be covered in the importing data into VPython and getting that to visualize. But the first thing that you should do whenever you get a program, even if it's something that somebody else wrote, just check and make sure that it actually seems to be working okay. So we'll just give this a quick run, and we can see that our object fell, which is exactly what it probably should do. And these are printouts of various things that we'll talk about in a moment. This looks like it's probably the acceleration. So we have an acceleration here due to gravity, and it should turn out to be about right. That could be wrong. I'll have to go and check and see what I actually printed out, but things looked reasonable there. So first of all, we're importing information or libraries of programs into VPython. Don't touch these. Then we get to the visualization graph setup. So you don't really have to change anything up here either for right now. So I'm not going to spend a whole lot of time on them. This is the scene. I'm calling basically a display window as a scene. So it's just going to make a window. Tells me where to make it, tells me how big to make it. So if you want to make your screen bigger, you can certainly do that. And it tells you how zoomed in or zoomed out you should be. So a large number here means that we're basically going to see more distance being covered. And for this particular purpose, I thought about 1.5 meters should be enough, because when you're actually dropping your mass, it doesn't actually fall more than about 1 meter or so. Alright, so I've made a box, and this is going to represent our mass, our hanging mass that's going to fall down. And I just put in some sizes here. And then I'm going to give it a trail so that we can see the color, or the path that it takes. I'll indicate the origin, even though that's not really that necessary. And I'm going to make some arrows where we can show off the forces that are acting on it later on if we want to. This part right here, this is where we're going to make the mass that shows us the actual video data that we're going to import in, but that's going to be a topic for the next video. So then normally what you do is, just like if you were solving a problem by hand, you would indicate what your givens are. And so this is something where you might have to make some modifications. For me, I'm saying that I used a 0.2 kilogram mass hanging off of the end. Here, this is the mass position vector, and this is the position in the x, y, and z directions. So this is x, y, z. And our coordinate system in VPython defaults so that x is going to be this way, y is going to be this way, and z will actually be kind of towards you and away, so into and out of the screen. We'll do the same thing for the velocities. Now, technically, it might make sense for all of these three to be 0, but it's going to depend, at least in part, on how you did your data. And likewise here, this should all be 0 as well. You can assume that it was 0. I mean, you should have been capturing it right from the start. So you can put in 0 for now. I'll tell you some more sophisticated methods in the future to deal with that, but zeros work for the velocities for now. For your positions, what you should do is you should go to your spreadsheet where you have the video data, the x and y position specifically of your hanging mass falling. So here's an example of what your video data might look like. You might have the times over here. You might have your x positions and y positions. Your x positions for the hanging mass should just kind of fluctuate around 0. Your y position should get steadily bigger and bigger and bigger, actually in the negative direction in this case. And what you would do is, if you didn't quite get this perfectly right, let's say that it ended up that you got it about 1 centimeter into the fall to start with. So what would happen then is you would end up starting with 0. Well, your initial x position would end up being whatever these two values are up here. So you would take these two numbers, even though I'm writing over top of them, but you'll take these two numbers and you'll put those in as your initial positions. So I think we had 0.0095 on this one, and oops, that's the z direction, and -0.01 on this one, I think is what I ended up getting. So we have these, our initial positions, put into our simulation, and that's just going to modify where it starts. Because I'm assuming that I made my origin of my coordinate system in my video analysis basically where the mass started falling, these should be close to 0. If you did something else, maybe you put your coordinate system on the ground, you'll get very different numbers out. But it's okay. My total time, this is something you're going to have to adjust. So if I go back and look at my spreadsheet, what I want for my total time is just the final time minus the initial time. And so I get 0.733333 seconds. So I'll just go back over and I'll make it 0.74. I'll round up. The reason I'm rounding up is because later on I know that I'm going to be doing a while loop. And I'll just fast forward a little bit. So when time is less than the total time, and if I choose some time that's less than this amount, then I could end up missing a data point. So I'm just going to, for the sake of making sure that I get all of my data points in, I'm going to make this slightly higher than the actual total time, since I'm not going to do an exact time. Now here I have G, and I want to talk about this just briefly. One of the things that I've been stressing in class is G is a positive vector. Or a positive number. So we always make it so that G is equal to 9.8 meters per second squared. And I want you to continue to use this. Basically what we're doing is we're saying that G is a vector, but I'm going to use the absolute value of it to be 9.8 meters per second squared. Always positive 9.8 meters per second squared, because it's just the magnitude of the vector. I do this because I think it's easier to handle it in this way, particularly if you're, say, dealing with force of friction is equal to mu times the magnitude of the normal force, right? We don't care what direction G is if G played a role in this normal force. Likewise, it can just kind of confuse the issue if we're dealing with G magnitude most of the time rather than G vector. Hopefully that makes at least a little bit of a sense. However, the VPython program only recognizes G as a vector in this case. Okay, this is to make life easier a little bit later on. We could totally do this in a different way, but I'm going to try to show you how this works out in this manner. In some ways, this actually, in some programs, this could make things a little bit more confusing, and we want to revert back to this method of treating G. But in this case, it's a pretty simple problem, and so I'm going to show you sort of the more advanced way to set this up. So the way that this works then, this is once again x, y, and z. And because VPython automatically defines the downward direction as the negative y direction, and gravity is going to be pulling this down, I'm going to make it negative 9.8 for my y direction. Gravity shouldn't pull in the x, and it shouldn't pull in the z. So this is why I've made my g vector like this. Later on, we'll see how this plays out with the forces when we calculate forces. So this is about all that I should really need to do. Make sure you update your mass, make sure you update your initial position, your total time, and your gravity vector. Actually, you don't need to change this at all. That's already set for you. The last thing that you need to make sure that you understand is this delta t. So these are our time increments, and we need to make sure that these are divisions of 1 over 30. So I've done basically 1 over 7 times 30 now. So what this is going to do is, for every one update of the video data, so we'll have our object here and then we'll have it here, what's going to happen is we're going to end up with, oops, that's not what I wanted to do. For every one update of our video data, we will have updates. We'll have updates to our actual model that we put into VPython 7 times. So 1, 2, 3, 4, 5, 6, 7, something like this. Hopefully it lines up a little bit better than this, but actually it probably won't, because we use 2 different methods of collecting the data for the video and for the model. But in any case, we want to make it so that they should line up if our data matches perfectly. And that's why we use increments of this. Why did I choose 7? Really just because I wanted to get enough increments of the model so that that iteration error that comes into play. So if it should be a smooth graph like this in terms of the position, right, where it's increasing its position over time, we don't get a huge incrementation error when we, oops, stop. Actually, that might not be a bad thing. When we take our little rectangles to estimate what's going on, we don't miss too much. So we want to go small enough that we get a good model, but we don't want to go too small so that we take way too long or anything like that. So that's going to be it for this video. I know it was a little bit long, but hopefully the things that are important for you to change, like your initial position and so forth, are clear to you now in terms of what we're going to be doing. In the next video, I'll take you through the part where we actually make the model run and update it using the physics.